Hi, everyone. Can I just get a quick audio visual check? If you can hear me, could you just in the reactions or just do a thumbs up or something so I know that you're able to hear me? Okay, I have a few thumbs up. Very good. Hopefully the others can hear me. Okay, I'm seeing a few thumbs up, but I haven't heard anything from the others. Hopefully you can all hear me as well. Give it a couple more minutes, see if more people join us.
I'll go in person on Friday.
All right. Hi, everyone. I'm Professor Gurudev Dutt. I am your instructor for Physics 1361. And I am coming to you from Oregon National Lab in Chicago. I'm just finishing up a research project here over the last week of the summer. Technically, I guess summer is over, but just had to. This was the last sort of available time window that I had with my colleague here, so I had to be here. So I apologize for not being in person um, in at Pitt this week, but I will be back next week. And I figured this first week is, usually fairly relaxed in terms of, what we are doing, both in the lectures and the lab. So I figured you wouldn't mind too much if we did this online, remote learning. Although I have to confess that the last two times I taught this class was both during 2020, 2021, when we were fully remote. And I thought to myself, oh gosh, I really don't want to do that again. And but here we are, and the first week at least, I am still forced to come to you remotely. But I think this will hopefully be the last remote lecture, and we'll do everything in the classroom in person next week. Okay, so again, apologies for forcing you to sit through another Zoom lecture, which I'm sure everyone has had their fill of over the last few years. But and I thank you for coming here on the Zoom session so that we can get this course started. So before I start, let me see. Okay, yeah, here it is. Screen to share. Okay. Hopefully you can see my desktop. just started that lecture, and you can hopefully see that. The slide. If you can't, just let me know in the comments or the chat. Okay, so let's just get through a few very basic things about the course. This is, let's see, how do I hide this? Oh, now that how do I hide this? Oh, sorry. You would think I should know how to do this by now, but okay. All right, I'll just have to put up with that little panel over there for now. Okay, so just a few quick basic things. This course, you already know the lecture and lab timings, and we will be meeting next week in 106 Allen during this hour. And the labs are in 306 Old Engineering Hall. And this week, you will be going to the labs where Dr. Danko, who is our lab manager and is a really great resource, is going to be taking you through a mini lab tour, showing you the setups that we have for you, talking about lab safety, and also a little bit, I think he's giving a small lecture on measurements and error analysis. So all of you should go to that, and that's in person in the labs. Our teaching assistant, who will also be helping with the lab, Benji Huang, his information is posted in Canvas, and you'll be meeting him as well this afternoon. Couple of other things. Presumably you already have these prerequisites for the course, and if you don't, then come see me or talk to me, and we can, I'll make a determination if you're able to take the course or not. Okay, some core requisites. Well, I mean, if you're taking these, that's great. If not, there may be some math stuff in the course that might be difficult. If so, please, immediately let me know, and we can discuss, or I can go into more detail with you separately, or do more of that in the class as well, depending on which parts are causing trouble. Okay, and the Canvas site. So actually, now that I have the Canvas site, talking about the Canvas site, let's see, is there anything else on the next page? Yeah, so before I get into this, let's go back to the Canvas site. Okay, that's good. All right, so here is our Canvas site for the course. Hopefully everybody has started looking at it, even if you haven't read it all, which I understand there's a lot of information in here. So, mainly I've talked a little bit about how the lectures are going to be conducted. I'm hoping to include a lot of active learning assignments during the lectures, so please attend the lectures, because we will have some quizzes or questions in the lecture that I'll try to make sure that you're following along with the course material. And my hope is that we can cover at least the basics of the physics and the concepts that you'll need in the lab. But the lab may not always be possible to synchronize with the lectures. It's just because optics is a vast subject. The labs move fairly quickly through the semester, and so it can be difficult to synchronize exactly. So if we are not quite at the point of discussion of that lab, then it is sort of your responsibility to at least glance at the chapter or the textbook and make sure that you have some knowledge of the subject, what's going on. And I'll come back to this when we discuss the lab notebooks as well. For the in-person classes, I request that everyone brings, some kind of electronic device that allows you to access the Canvas, because we might need to access that during class time to turn in any work that you did in the class. Okay, on the textbook is Introduction to Optics, 5th edition by Eugene Hecht. This is the 5th edition, and I'm aware the cost of this textbook is fairly high, but a lot of the material is the same as in the earlier editions. So if you want to just pick up a 4th edition or something, that's probably going to be fine. But when I do assign problems, if I just refer to the problem number, you're going to have to make sure you actually look up the right problem from that 5th edition. So just letting you know, there's also an ebook via Red Shelf, which is significantly cheaper. I can supply details. If anyone is interested, just contact me. Okay, the course, logistics, there'll be about 3 or 4 exams, roughly every 5 weeks or so, 4 weeks, I guess, if I do 4 exams, and including a final week. So there'll be a final exam as well. All the tests I'm planning to administer as 24-hour long take-home exams. So once the test is assigned and it's available, you'll have 24 hours to finish it and submit it back on grade school. So there won't be any in-person exams. You'll just work on them outside of class. And as I say here, even though each test typically will cover a certain portion of the syllabus, except of course the final, which will cover the entire course. But as we progress in the material, material from later parts of the course will build on the earlier parts. So it sort of will keep retesting concepts that you have learned in the beginning part of the semester and in the middle and so on. So, but since it's take home and usually I make it open book, you'll have access to the textbook to look at stuff. So, hopefully that will resolve most of the issues. Homework will consist of questions that are associated. I said lecture videos, but associated with the lectures, and as well as problems assigned from the text or lab manual. I'll try to build in some time where we work on problems in the class. Usually, instead of me just trying to solve the problem, which, there will be some of that, doing some examples, but also I'd like to include some group work with classmates, and, hopefully we will have the time to do it. It's always that things tend to, I will be honest, like in the beginning of the semester, I'm pretty good about it. And then as the semester progresses and, things start to, I have to try to keep up with the lab work as well. Things start to go a little bit more rushed. So, but we will try to build that in because it's so important, I think, to keep working on problems and figuring out where you're having difficulties. Okay, as I said here, even if you just attempt the problem, there will be some credit given, which will also serve as attendance for the lecture. And of course, then there'll be some extra credit for or you'll get the full credit 100% if you solve the problem correctly. Okay, then probably the biggest part of the course, in some sense, as you can see down here, I'm just jumping ahead a little bit, but your course grades are based, in large part on the lab reports. Of course, the tests and quizzes and all that count for also a reasonable fraction, but the lab reports are obviously a very significant fraction, considering that there are 9 of them through the course of the semester, and they have to be completed by all of you, everyone. And but for most of the labs, except maybe lab 0 is the one difference, because that's mostly just done on your computer. Your work will be all on a computer or turning in a homework assignment. Except for lab 0, all the other ones you'll be working typically in teams of 2. And you'll see this afternoon when you get into the lab how that works. We have, I think, 6 or 7 setups for each experiment, and you will pair up. We may have a few more people so in that case, there might be, teams of, sorry, I scrolled ahead there. There might be more than, 2 in a setup sometimes depending on how many setups Dr. Danko was able to create that particular week. Okay. If you miss a lab for some valid reason, which I will, you're sick, you have some urgent doctor appointment, or you have a doctor appointment that couldn't be rescheduled, or obviously if you're sick, please stay back, don't come in. And, you will have a chance to make it up. Dr. Danko is very available, very helpful. The TA also is available. We can't always promise that the TA will be there to help you, or I will be there to help you during the course, but Dr. Danko is usually around to give some hints and help. So when you do the makeup labs, you'll have to schedule that usually with Dr. Danko to make sure the setup is available. And also, I think we'll have 1 week in there once I make the course calendar, which I haven't quite filled all the dates in just yet. Once I have the course calendar up, then you will see, which weeks we have for which is just pure makeup, meaning that you can come in and do makeup labs. Okay. So besides these 9 standard labs 0 through 8, by the way, I've been talking for a while. Does anybody have any questions? If you want to, speak up or raise your hand or something so that I can, let's see. Is anyone raising their hand? No? Okay. So, all right. All right, so no questions so far. All right, so so in addition to those 9 standard labs, as we call them, which will have pre-existing setups for you and so on, you also get a chance to do special projects, 2 special projects that will be completed in the last 4 weeks of the term. And those, we only have 1 setup typically for a special project. So, but we have like 6 or 7 or maybe even more, I forget exactly. But starting around probably lab 6 or lab 7, we'll post all the special projects and schedules. I'll post like a page where you can like sign up, a sign up page. And then, you have to, with your partner, lab partners, pick 2 of them, and it's a first come, first serve. Whoever signs up first, gets that particular lab. We can work around sometimes, like, depending on how quickly some of the labs get done, we may be able to make it available for more than 1 group, but yeah, it's all on a first come, first serve basis usually. Okay, and we'll have more details about how the lab report works and how we'll be grading it. I'll post rubrics for how we grade the lab notebooks, etc., so that you get a chance to look at that later on. This first week, as I mentioned, is a pure computer-based assignment with with maybe some calculations that you'll be doing. So it's not like our typical lab notebooks. So you don't have to. It'll be more like a homework assignment this first week for the lab. Okay, so I already talked about the assessments. Percentage for homework is not very big, only 15%. But if you don't try the homeworks and give a good effort on them, you're going to probably have trouble on the tests. So I strongly suggest you try your best to work through the homeworks carefully on your own. You're certainly free to discuss them with your friends, but you should attempt them on your own at first and try it. And then after that, you can, talk about it with your friends and see how to solve it. And of course, you can always come and talk to me in office hours and or the TA, etc. And we will, are happy to help for those things. In addition, I have some extra credit assignments, and you'll see these get posted during the semester, and they will be used to account for about 5% of your extra credit grade. So, as I mentioned, in principle, this means you could get 105% on your final, as a final total score. Or equivalently, you can drop 1 lab report and make up for it by doing all of the extra credit, for example. So there are built-in ways here so that if you miss a lab or miss a lab report, it's not the end of the world. We have ways in which you can make it up, but obviously you should take the initiative. If you miss a lab, try to make it up. But in addition, we have these other options as well. Okay, so these are the labs. I'm not going to say too much about them right now. Just you're showing all the different labs that we're doing, lab 0 through 8. And then here is a list of the special projects. This is somewhat tentative. We are, still deciding. So please don't take this as the definitive list of special projects. That will be posted in more detail towards towards that time when we get to that point in the course. Okay. So the lab manuals, lab schedule, all this will be posted typically under the modules section. You can see that right now, I have it posted, but, we don't, you can see here, Dr. Danko has posted already some of the basic lab safety and intro to measurement and all that stuff. So this is basically what you should be seeing, I think, right now under the modules part of the Canvas page. Okay. Again, I'm not hearing any questions, so I'll just keep going. Okay. And okay, these are some standard, statements about the honor code, academic integrity, code of conduct. I expect everyone, because this is going to involve a lot of teamwork in this course. You're going to be having lab partners, and you're going to be working in groups, even in the class. So it's very important to maintain, communication and respectful and honest and communication, which we do not in any sense tolerate, and it's unacceptable to harass or discriminate or abuse anyone because of all of anything, essentially. Okay. Again, another statement about disability resources. So if you need special accommodations for the test, as I've said, I've already sort of made all the test take-home exams. So in some sense, I think this probably takes care of those issues. But if in addition you need something else beyond that, then please reach out to DRS, and then they can contact me about that. All right. Okay. More stuff about Title IX. All right. And then we come to the lab reports. Again, I'll post rubrics, and I'll go into more detail on this. Probably next week, you'll have your first real lab, so to speak, the lab that requires you to carry out, optics experiments. Oh, wait, I have a question in the chat. I don't have access to the Canvas site. I see. Yeah. Okay. I will add you after this class is done. Okay. Send me an email, because if I lose this chat or something, I'll forget who it was that sent me this message. So please send me an email, and I will add anyone who doesn't have access. So the main thing you need to know about the labs and preparing for the labs is that we have a pre-lab that you need to complete before the lab session. So that means when the lab manual will be posted in advance of the lab. So make sure you look at the lab manual and read through it. And the pre-lab should have some basic, like 1 page is really all I expect from the pre-lab, okay? You should have your title of the lab, the objectives of the experiment, and essential theory, meaning you just need the formulas that you're going to be using in the lab. You don't need to derive them. You just need to write them down so that you know which formulas you'll be using. And then a brief outline of what are the main experiments you're going to be doing and what results you're expecting to see. Okay? Please don't copy and paste the material from the manual. That will lead to point deductions. Okay, so we expect you to write it in your own words. Yeah, so as I've just said here, working equations, if you can, this is probably will get you the full marks if you give examples of data analysis and dummy data and all that stuff. For example, if you're plotting angle versus, input angle versus output angle for, say, refraction lab, then if you plotted some dummy data, this is the kind of data we are expecting to see, yeah, that's certainly very nice, and we'll give you the full points on the pre-labs. Okay, so that's all you're expected to do before the lab, and then during the lab, yes, notes and stuff, and I'll talk more about this in the class next week. But that's where will be the bulk of what work that you do. So again, as I said, for the pre-labs, like 10 minutes the day before, if you spend 10 to 15 minutes the day before the lab, just looking through the lab manual and making one page right out, that's usually more than sufficient to get you like 80% of the grade, right? So the notes, yeah, they're as I said, I'll talk more about this. Probably the biggest thing I should mention is making sketches of the setup, by which I mean, yes, you can take pictures of the setup, which is, that's great. But a lot of times people just take a picture of the setup and just put it in the document or in their lab notebook, whatever pages that you're writing on. If you're doing it by hand, that's perfectly fine. If you're making a sketch by just like sketching in a piece of paper, as long as the sketch is neatly labeled, and I'll show you some examples, as I said, next week. But that's probably one of the biggest things that we look for, is that you have a clear picture of your setup, a sketch of your setup. Pictures of the setup are great, but if you have a picture, then you need to like point to like what is what, like where is the laser beam coming from, where is the where is the lens, where is the image being formed, whatever, right? I mean, this is very important, because otherwise it's just a picture and nobody understands. Nobody who doesn't know something about the experiment will understand what you're talking about. So the key principle to keep in mind when making your notes is to just ask yourself, is it detailed and clear enough that other people can follow them? Or if you yourself would be able to make sense of your notes a year later, right? Or even 6 months later, you'll be amazed, right? If you look back at like your notes from 6 months ago, even, maybe you took some lecture notes and you're looking back at it, and if you didn't do a good job, you're like, what does this even mean, right? I've been in that position sometimes. If I was taking lab notes and didn't do a good job, I can't even figure out what I was doing. So that's the kind of thing that we're looking for from you here, is that you should be able to make things easy to understand for yourself and for your TA, because if the TA cannot easily understand the notes, then points will be deducted. Even if your work is correct, even if you got great results, we still need to know that you took good notes and you made sure that you were following good procedures while you were doing the experiments. Okay, I'm going to stop talking about lab notes. Again, as I said, I'll come back to it. But essentially, the grading of the lab notebooks, it's worth 50 points. We divided up like 10 for pre-lab, 25 for notes, 15 for analysis. Okay, I have another question. Oh, no, that's it. Just one question. Okay. All right, lab safety. You'll hear a lot more about that this afternoon, so I won't go into that, in this lecture here. Okay, I'm going to stop sharing this particular screen and go back to the PowerPoint. Okay, all right, hopefully everyone can view that. Yeah. All right, so let's now talk about our objectives in this course. It's always important before we start on any new endeavor to kind of have a very clear picture of where we are going, what we are trying to achieve. So the lecture part of this course, in the labs, you'll be doing experiments, you'll be, learning good procedures for experiments and in optics and understanding how optical phenomena behave. But in the lectures, we're going to be covering the theory and the physics of those experiments by understanding the fundamental properties of light propagation and interaction with matter. Okay, by the way, I didn't ask if you can see my cursor here. Let me see. Okay, hopefully you can all see this laser pointer. Okay, and there are two major sections into which optics is divided: geometrical optics and wave optics. And wave optics is further subdivided into scalar wave optics and vector wave optics. Scalar wave optics essentially treats light as a scalar field, And vector wave optics takes into consideration that light is actually an electromagnetic wave. So it consists of electric and magnetic fields. And these electric and magnetic fields are vectors because they have, I'm sure you've all had some introductory electromagnetism. You know that there's, different components of E and B. And so that matters when it comes to certain phenomena, such as polarization of light. Okay. Our goal is to both develop the physical intuition as well as gain familiarity with the mathematical tools, of course, for this being a physics class. And I think
so,
also,
excuse me. So
yeah.
I'm wondering if I have some experience in solid state physics and many body physics. So is that helpful or related to this course in terms of the solid state physics?
That's a good question. I don't know what your solid state physics course you took.
I took the grad solid states with David Snoke, and in the chapter of his book, he talks about some the Raman spectroscopy and the many body background for that. Right.
No, I mean, we aren't going to go that far as many body physics or anything like that. I mean, this course is the introduction to optics and wave phenomena. So we start by covering things like geometrical optics, and then we move on to wave optics. So you can think of this as we're going to take maybe the wave phenomena that you read about, and we're going to apply it to light, basically.
Yeah, and it's like E&M we talk about the polarization vector stuff.
Yeah, we will get to that later in this course. Yeah, we'll talk about polarization. We'll talk about various devices to like measure polarization, manipulate polarization. It's the same with, how do you manipulate light? How do you set up a Raman, for example, you talked about Raman spectroscopy. How do you set up a Raman spectroscopy experiment? Well, you need like lenses, you need lasers, stuff like that. So that's the kind of stuff we are talking about in this course, and understanding how those things behave. But just down here, as you can see, we are applying many of these concepts also in the homeworks and in the and in the discussions of the material. I'm going to try and sprinkle in a lot of applications because that's where really you start to begin to appreciate the beauty of optics, which is all the various things like optical microscopy, astronomy, optical switching and routing, lithography, visual perception systems, instruments, all this stuff. You can begin to appreciate them more once you have a deeper understanding of these topics in optics. Does that kind of answer your question?
Yeah. So do we have time to touch some code atoms, some AMO physics?
No,
matter theories?
Probably not.
Yeah, my background is condensed matter theory. Yeah.
No. This course is not really meant for that. You probably want to take a quantum optics course. I teach a quantum optics course, but not next semester. So, somebody else might be teaching a quantum optics course next semester. So you probably want to take that course if that's your main interest, cold atom physics. Yeah. Okay. All right. And learning outcomes. So we've talked about objectives for the class. Now we should discuss, what I expect that by the end of this class that you will be able to achieve and will be able to do fairly comfortably is to be able to describe optical principles of how lenses and mirrors and instruments and work and their limitations as well. And obviously waves, light is a wave, and that's a big part of this course. So we will be using wave motion and superposition to explain the physics of various topics like interference, diffraction, and polarization, as I already just mentioned. And then there are many optical devices that we'll be introducing during the course, such as polarizers, wave plates, modulators, interferometers, etc. And so by the end of this course, you will understand how these various devices work and be able to describe what they do. And of course, being a physics course, you should be comfortable with understanding what a particular problem in optics, which equations or which concepts apply to that problem, and performing the appropriate numerical analytical calculations. Then, as I already said, a large part of this course is laboratory experiments. as you can see, the amount of time you have in the lab is more than the amount of time you have in lecture. And so we expect by the end of the course, you are very comfortable in, following procedures and protocols in optics labs, documenting the results, and performing those experiments. And of course, also being able to analyze and interpret and communicate those results, both orally or in written lab reports. Speaking of written lab reports, some of you, I think, are probably also signed up for Physics 1661, which is the written, writing practicum course. That is, if you sign up for Physics 1661 and select me as the instructor, then mainly what it means is that the writing assignments that I'll be giving you, which are different from this writing assignment. So the writing assignments that I'm talking about in this particular slide are entirely just to do with the lab notebook that you're turning in for Physics 1361. But if you take 1661, you'll have a separate written requirement that I will discuss with those of you who are in Physics 1661 later on. So that's a whole separate course. It has separate requirements. It has separate written assignments because we are trying to teach you how to do scientific writing in that course. So please don't assume that just one, lab notebook that you're turning in for this course will be enough for that course as well. That's a whole separate course and has different requirements. And I'll come to that when I probably next week, I'll start sending out some material about that. Okay, so what are the sort of things, we've talked about prerequisites for the course, but here are some of the things that you should be comfortable with as we progress through this course, because we will be using these math techniques pretty often in this course. So elementary, Euclidean geometry, like, triangles, similar triangles, congruent triangles, basic stuff like that, parallel lines and things like that, that we'll be using that when we derive equations for ray optics, trigonometry, of course, because angles and stuff are very, going to show up a lot. Later on, as we get into interference and diffraction, we'll be manipulating waves using something called phasors, which are basically just complex variables. So if you have some basic knowledge of complex analysis, complex algebra really is all you need for this class. You don't need a full complex analysis course, just complex algebra. Well, and I will introduce some of that as well in the class, but it's helpful if you already kind of know it, because we don't have time to do a full introduction to complex algebra. So you are expected to sort of have some basic knowledge, and we'll refresh it in this class. And as I said, when we get into even waves and vector propagation of waves and stuff, you should have knowledge of these calculus, 2 and 3 dimensions, and some basic vector analysis. Taylor series, sometimes we're expanding things to get to the small angle approximations. So hopefully you all have seen that several times. And then for the lab courses, when you carry out data analysis and plotting things, it's often helpful to have some knowledge of some, software like Mathematica or Python for simple computations and visualizations. Excuse me. And, I assume everybody has had a basic, 174, 175 level type of course. So you kind of already have been introduced to electromagnetic fields and the laws of electromagnetism. And that's put together as Maxwell's equations. If you haven't seen them before, we will introduce them, but if you've seen them, that's always a nice thing. Hopefully you've also seen some basic wave propagation. If you haven't, please let me know. But anyway, we'll be talking about it in this class. But again, it's always better if you've already seen it once, and then we are starting to again, go over it, kind of sinks in more easily, a little bit more easily the second time around. And Fourier analysis, I don't know how much I'll have a chance to do that. Hopefully towards the end of the term, we'll introduce Fourier optics. But, that's something that remains to be seen, how much time we have left in the class by that point. So if you have done some Fourier transform, Fourier series before, then it's helpful for that. I don't expect to use it a whole lot. I'll make some references to it maybe. Okay, I think I already talked about much of this in the syllabus, so I'm not going to go over this. besides the textbook itself, here are some additional textbooks. So if you feel that a textbook here does not cover material in the way that you need, then here are several other textbooks that I found helpful. I sometimes use their material when I'm supplementing from, in the lectures from Heck. Okay, yeah, I already covered all this, so I won't go over this. Already covered this as well, so not going to talk about this. I've covered the lab, so okay. So looks like we're sort of ready to talk a little bit about today's physics material or introduction to physics. This is just a list of all the topics that I hope to get through by the end of the course, up to Fresnel diffraction for sure. But if time permits, as I already mentioned, Fourier optics and spatial filtering, more interesting stuff like holography, nanophotonics, metamaterials. Very ambitious. I very much doubt we'll have a chance to talk about this, but this material that you learn in this part of the course makes a solid background for you to explore some of these topics on your own, if you're interested. Okay, I'm going to pause briefly. Any other questions from anyone? Okay, so let's talk about light. Light, is everywhere, right, around us. I mean, a large part of the human brain is taken up to the visual cortex and processing the signals that come from our eyes. That kind of tells you how important light has been to human evolution. And starting with, the science of things like rainbows and double rainbows, some of which we will talk about in this course, to looking at up into the sky and wondering what all those little points of light were. Humans have always been fascinated by optical phenomena. And as mankind has progressed, we have learned how to build devices that go beyond just what we can perceive with our eyes. And we can use, optical instruments like microscopes, telescopes. We can even build systems that are not present in nature, such as a laser. And things like, using optical lithography to improve the amount of information. We could fit like huge numbers of books onto a single CD-ROM. I mean, CD-ROM probably most of you have not even seen these days. This is like old technology now. But yeah, so this is kind of tells you like how much light has mattered, both for the progress from biological perspective has allowed us to make the human brain kind of, evolve, but also from a technological perspective is allowing us to explore the universe in many different ways and build technological devices that we previously had no access to. So here are some natural imaging systems. Obviously, the eye, we'll spend quite a bit of time in this class also on discussing how the eye works. And but probably many of you are familiar, there's a lens in the eye that focuses incoming light onto the back of the eye where there's a retina, and the retina then it has detectors essentially in there that are sensitive to light, very sensitive detectors. In fact, we'll talk about this more. And then that is then those signals, those voltage signals essentially are sent through the nerves into the brain for processing. And here is a compound eye. A compound eye consists sometimes of just like retina-like cells, like, just detectors, or maybe a lens with a detector, but multiple of them. And then the brain of the insect puts together all these different images to navigate its environment. And as I already mentioned, we have built now by gaining understanding of how electromagnetic waves and light propagate, we've learned how to control the propagation of light to image systems, small systems. This is still with light, visible light, and far away objects using telescopes from the Allegheny Observatory. And then we have extended the wavelengths. So this shows like a radio telescope. we can now image the galaxy, for example, using radio waves. There are so many ways, even on Earth, for, I'm sure you're all heard of radar, which is just, again, using propagation of electromagnetic waves in the radio frequency range to detect objects. This is an outgrowth. I mean, radio telescopes are basically an outgrowth of radar research that happened during World War II. But in telescopes as well, we have extended, the wave range of wavelengths. So besides radio telescopes, there are X-ray telescopes and gamma ray telescopes and so on. And in the optical domain, in the microscopy domain, I've talked about, optical microscopy, but there's also electron microscopy, X-ray microscopy, et cetera, et cetera. So we've extended sort of, because our light, the eye is only sensitive to a limited range of wavelengths, frequencies of light, and of electromagnetic waves. And we are now extending that out into very different domains. So a brief history of optics, I guess, is very kind of, I think, very interesting to me, at least, which is that as far back as 2000 BC, the Egyptians were already using mirrors made from like polished metallic surfaces. The Greeks in 300 to 500 BC, they were very interested, primarily more in understanding the theory of light. They speculated, Pythagoras, everybody knows his name from your elementary school, I'm sure. And he speculated that rays are coming out of your eyes and hitting objects, and that's how you perceive the world. And Plato, Democritus said, no, it's the other way around. Objects emit some kind of magic substance that is then perceived by the eye. Plato was a consummate politician, I guess. He combined the two. He had a theory of his own. Aristotle thought there was some kind of vibration that was being transferred between the object and the eye. Very interesting, sort of presaging kind of wave optics, perhaps. But probably the most important thing, besides these sort of essentially philosophical speculations, Euclid was one who, again, in catoptrics, just like his elements, he investigated reflection, and he realized that there is a law of reflection that he could postulate, that he thought that all reflective materials, really reflective materials, obey, and he was right. So that's the first example of a law of reflection coming out from sort of experiments that he did. And there are many others in the Greeks. Then for a while, a long time, really, 1,000 years almost, pretty much nothing got done in optics, as far as I can tell from looking at the history. But then in the Middle East, there was a big sort of, while the Western world was going through sort of the dark ages, there was a flowering of science and so on in the East, in the Middle East and beyond, in the Eastern continents. And Ibn Sahl is famous because he, 1,000 years before, or maybe not 1,000 years, but many hundreds of years before Snell postulated the law of refraction, Ibn Sahl already had understood how refraction works, which is, pretty amazing. And he also derived the properties of many mirrors that are not just spherical mirrors, but of shapes of like parabolic and ellipsoidal and hyperbolic. Then these are devices that we have only now recently, in the last 50 years or so, really been, or maybe 100 years or so, been able to fabricate these kinds of devices. And others who are very famous, Alhazen, and Al-Kindi wrote many, many tomes on, thousands and thousands of pages on optics. And they defeated this emission hypothesis. They showed that, this idea that bodies are emitting some rays, that rays are coming from the eyes, they showed that was not true. And Alhazen, again, in particular, also studied spherical and parabolic mirrors. Finally, it took till the 12th century AD for someone to invent the lens, but they still didn't really understand how the lens worked, but they invented it by accident. I think we don't know who it was. It's lost in the history books. And finally, I think Leonardo da Vinci and Della Porta were the ones who first came up with maybe what we might think of as the first camera, the pinhole camera or the camera obscura, to take pictures. or at least to let people look at faraway objects and image them sharply. Okay, so in the last couple of minutes, just quickly, I will cover sort of the entire last 1,000 years, maybe, or several hundred years. We had many famous scientists. Kepler and Descartes formulated geometrical optics, explained lens behavior, and constructed some optical instruments. And the first sort of, we now give credit to Lippershey and Galileo for inventing the telescope, and Janssen and Fontana for inventing the microscope. My suspicion is it had already been sort of invented by other people, but we don't have the record of these inventions anymore. Newton and Huygens were by this point fighting already over the nature of light. This is a fight that I'll come back to in the next lecture because it's very interesting. It's a fight that, to my mind, it sort of has continued. It seemed to go away for a while. It seemed like Huygens and Fresnel and Young were the two people who showed that light undergoes diffraction or interference. It seemed to completely defeat Newton's theory. But then it came back because of various effects like the photoelectric effect and Compton effect and various things that we think of as belonging to the quantum world in the 20th century. That sort of has brought back the particle picture of light. So we always have this tension. That's because light is a quantum field ultimately, and this sort of tension between the behavior of light, because it's zero mass particle as a photon. You might have heard of this if you've taken any relativity class or something. So because of that, we are able to perceive both of these aspects, both the wave nature and the particle nature sort of simultaneously in light more easily than we can with other particles. Anyway,
so here, are you talking about we are doing the second quantization to the electromagnetic field?
Yeah, I am not going to cover that, but yes, you are right. That is what I'm talking about, in the sense that electromagnetic waves behave as a quantum field. So their excitations are what we call photons of that quantum field. But again, that's meant for somebody who has taken, quantum 1, quantum 2 grad level and is going on to quantum field theory, for example. We are not going to talk about that in this class. I might refer briefly to little hints of it here and there. Let's put it that way. But that's not the focus of this course. Okay, so what does all that buy us? Well, we've had many things come out of quantum theory. We've seen in the 20th century, as I mentioned already, holography, the laser, and proliferation of optical applications. We've already shown some examples, but in communications and computing, everything from your laser, checkout. When you go check out at the grocery store, you have these laser scanners. To fundamental science, medicine, laser surgery that we do, manufacturing. There are laser machining things. I'm talking about laser specifically, but things about like fiber optics. All of this is, I'm sure you've heard these terms, and they are all all around us. Everything. The internet is nowadays built on the backbone of fiber optic cables and optical communications.
So here you said the holography. So is holography a more like the universal meaning? I know in quantum field theory or string theory we have the ADS-CFT stuff. Right. We calculate the correlation function in conformal field theory on the surface, and then we get n+1 dimension property of the bulk of the bulk. And that's also
again I'll reiterate, this course is an undergraduate course, so we are not going to cover any of that. I think the holographic principle that you're referring to, which comes from CFT and all that stuff, that was inspired by the analogy to optical holography. So in optical holography, let me finish. In optical holography, what we do is we take a 3-dimensional object, and by scattering light off of it, coherent light, we build a 2-dimensional pattern. And so we say that the 2-dimensional pattern that we capture has all the information about the 3-dimensional object in it, if you illuminate it correctly. Okay, so that is the whole idea of holography. in a nutshell. I'm simplifying vastly here, but that's the basic principle of it. And once we do Fourier optics, I'll be able to discuss that more. But let me just finish. So that stuff has, that idea of it is seen in conformal field theory, where they talk about, string theories on n+1 dimensions being, or sorry, whatever. I think you know what I mean, like where gravity shows up if you go to the boundary or something like that. Anyway, I'm not going to talk about that in this class. Okay, that is meant for an advanced quantum field theory or string theory class, not this particular course. Okay, so I'm out of time. We're already past time, so I apologize. I just want to finish with this one little slide. This is your homework assignment for today. Outline the history of optical phenomena in your own words and submit via Canvas. I'll make that assignment available, and I'll give you a deadline to by Friday or something. It's not a very difficult assignment, so I'm sure you can fill that out quickly. And I also will open up a discussion, which I think is very interesting, because I know of some optical instruments that were present in ancient Indian civilization. But I'm curious to know about other civilizations, and I'm sure Google is your friend to discover, besides just the Western, because I've kind of focused on the Western development of science, but I think there was a lot going on in other cultures and other civilizations that is kind of glossed over a lot, and I am curious to hear what you can discover on that. All right, so I'm going to pause here, and I thank you for your attention. And for Friday, there won't be a lecture, Zoom lecture, because I'm going to be flying out that afternoon. So, but what I'll do is I'll post a couple lecture videos, and we will go, and you'll have like a little assignment for them. And then what I'll do is next week, we'll go over them. I know sometimes it can be hard to follow up, but there will be some assignments associated with that, which will hopefully help you to work through that. And but if you have questions on that, we can talk about it in the next week's lecture when I'm in person. Okay, all right. Thank you, and have a good rest of your day. Thanks.
Yeah, you said
I can stay for a couple of minutes of questions.
Yeah, so you said there will be a quantum optics class. So is that the many body based stuff?
Quantum optics does not tend to be many body physics.
Yeah.
Quantum optics is a separate field.
Mm-hmm.
If I were to best describe it, it's really about ultimately it's a study of open quantum systems.
Yeah.
So we want to describe like quantum. Quantum second quantization. You've already read. You've seen it. It's not that difficult at some point, at some level, at some point. But but once you get past that, the real sort of interest in quantum optics is, especially when it comes to these days with quantum computing and quantum communication, and even cold atoms and things like that, quantum simulation.
Yeah, I read
a lot of. Sorry, let me finish. You asked me the question, so I'm trying to finish my what my thought is here, which is that a lot of these systems, quantum computing systems, quantum simulation systems, they are described as qubits which are coupled to an environment and to other qubits. And so describing the time evolution of these systems is a topic for quantum optics, basically. Okay, now what is your next question?
I read about Mikhail Lukin's work on the quantum sim. He was using a quantum simulation for the evidence for spin liquids that Anderson predicted in 1970s. That's a big news. So 1 year ago, is that part of? So is that the application of the quantum optics? So he was simulating.
I can't remember exactly which paper. I know they have had a few papers come out about this, but again, as I said, that's not the topic of this particular course. That's more a research area, topic.
Yeah. So
I can't remember now if there was quantum optics. In some sense, there is always quantum optics built into those experiments, because you're dealing with Rydberg atoms that are, in some kind of lattice. But I don't think that's the focus of that paper. That paper is more, as you just said, is more a realization, a simulation of the Hamiltonian of a spin liquid on a Rydberg atom qubit in a lattice. So that has more to do with, manipulating the potentials and the interactions between the qubits, for which, of course, again, as I say, there's always some quantum optics there. To understand the full experiment, they have to simulate, when they carry out some simulation to try and understand the experimental results, they are including some master equations and things like that to understand the full data. To simulate the data, they have to include decoherence, they have to include effects of laser light and scattering. So that's where the quantum optics pictures, the quantum optics knowledge comes in.
Yeah,
Does that help?
Yeah, that helps. For me, my research interest is in the quantum field theory of the strongly correlated systems. So I took.
So I'm not sure why you're in this course, because this course is way below that. If you're a theory person, then this course is not suitable for you. Although if you need to fulfill some theory requirement, some experimental requirement, are you an undergrad or a graduate student?
I'm an undergrad, so I have
an undergrad, and you've already taken quantum field theory and stuff.
Yeah, 1 and 2, and many body and many body physics and the grad solid states, and this semester the general relativity and the Lie group and the algebra.
Which year are you in? Senior or?
I'm a senior. I'm a senior. So I work with.
But I think you need to take one lab course, so that's probably why you're in this course. But this is very, the way as I explained it, this course is all about understanding light. Which in the theory you will have no trouble, because it's going to be very basic stuff compared to all the other material that you mentioned. But when it comes to experiments, that's where you may need to learn how to work with optical devices and instruments and lenses.
So I think
I apologize. I have to run right now. So if you have any other things, we can talk about it either next week, or you can email me separately or something like that.
Okay. Thank you.
Right. Have a good one. Bye.